Thank you. This was a very collaborative project between Stanford, Juan Santos at Heart Vista, Chuck Dumoulin, who gave us some tips on MR tracking, and Insightec, who helped us a lot with how to control the ultrasound transducer. So the purpose, let's see if I can go forward. While free-breathing liver treatments are very desirable, they're very complicated. Motion complicates the thermometry, motion complicates the targeting, and the ribs complicate the access. So the purpose of this work was to explore how we might do free-breathing treatments because we think they are desirable, that would allow us to be less invasive, maybe decrease the anesthesia. So what we're going to do is explore how to do the procedure with a handheld device and with real-time imaging and control. So for our methods, we use the Insightec bone transducer operating at 0.5 megahertz. We positioned this subcostally. It does have integrated tracking coils, so we were able to track where the position was pretty rapidly. It also has many elements that we could control electronically, so we could steer the beam as needed during free breathing. It's not an ideal frequency for thermal ablation of the liver, but we thought it was a reasonable test bed with respect to trying to organize how to deal with the motion and tracking and steering the beam, and et cetera. So on the MR side, we used a 3T scanner. We used a number of scout images, initially gradient echo, and then we settled on the SSFP because it gave us really nice depiction of the vessels. We used MR-RFI images, as I will show you. We used thermometry images that are based on EPI, and at times we used a readout segmented EPI when we wanted a larger field of view. For the processing, we used a hybrid multi-baseline reference list processing, and I'll show you some results on that. And then we didn't use the Insightec software at all, but we used our own that we wrote. This was built upon RT-Hawk, and that allows us to have real-time imaging and control, and through the software we're able to control the ultrasound transducer and the beam steering. It was equipped with multi-touch capabilities, and what we see here is a background image, one of the scout images that was a gradient echo image that was acquired, and then on top of that is a rectangular field of view that's being manipulated in real time. And what you see within the rectangular field of view are the real-time images that are required between 3 and 8 frames per second. They are done with a single-shot EPI and superimposed on that background scout image. So you can see as you look inside that rectangular field of view, there's a little bit of lag time because those are real-time images and there is a little bit of lag. And you can also see that there's a little bit of distortion because of the single-shot EPI images. All right, so we scanned a number of volunteers with this system. In addition, we did 3 porcine experiments. There's a number of different aspects to the procedure, and so what I'll do is this is sort of a timeline or the different portions of these, and I'll put these up at the top and highlight which one that I'm talking about, and we go from left to right. So the first part of this is that we did place the transducer in a subcostal approach, and eventually we'd like to be able to place it over the ribs, but we're not at that point yet. The first thing we did was modify the coupling based on the reflection data. And so you see 2 images here. And the first one, the reflection data, is showing you that there's quite a lot of reflection because you'd really like it to be all in blue. And when that happens, then we're just not coupling very well. And so we'd go back and reposition the transducer to get better coupling and get something like you see on the right. Okay, and the next part is to target. So we acquire multiple background images at different points in the respiratory cycle. And in addition, we obtain the transducer position at multiple points in the respiratory cycle. So our subjects are equipped with the bellows. At that point, we have background images that we can then highlight what the treatable area is because we know what we don't do this from the depiction of the transducer, but we do this from the location of the tracking coils, which we know, and therefore we know what the treatable area will be. And then you can interact with the volume. You can see there's multiple scouts and multiple scan planes, and so we can do that treatment planning in any image. All right, the next part is to target our tumor. And all we really need to know for beam steering is the position of the transducer and the position of our target. Unfortunately, both of those are moving with free breathing. So what we do is during the setup portion of the procedure, we acquire the bellows information. So then we can relate the transducer position at all points in the respiratory cycle to the bellows position. In addition, we relate our target position to the position of the vessels that we track in the background images that we acquire before the procedure, and then we can relate those to the bellows position. So that when we come back in real time, we can get the bellows information very, very rapidly, and then we can, through this information we've already gathered, be able to relate the bellows information to the transducer and the position as well as the target position, and that tells us about our beam steering. Okay, so let me tell you a little bit about tracking the vessels. So we get our SSFP images. We do this over multiple points in the respiratory cycle. And once we've acquired multiple images then over the respiratory cycle, we come back and we specify which vessels that we want to track. And so you see that there's a color there overlaid on the vessel that we're tracking. All right, so we track the vessels on the background images, and we superimpose the vessel tracking on our real-time image. So what you see in the rectangle is the real-time image, and on the back is the background image. So those were acquired some minutes ago. They're cycling with respiration, which we know because of the bellows information coming in. So you can see the two yellow dots there. Unfortunately, okay, you can see the two yellow dots there, and then one up here that are tracking different vessels in the liver. And what we can see is that they have a reasonable correspondence to the motion of the vessels that you can see in the real-time image. So that's giving you a good idea of how well we're tracking the liver motion, and therefore how good our beam steering will be. We do need to go back and quantitate that a little bit more. All right, at this point, we can do some fine-tuning of the procedure. And so the first part is to collect some RF images. So it's going to take a couple of respiratory cycles, and while that's happening over there on the left, what I show you here on the right is what the images would look like. So here's an RF picture, and it was specified that we wanted it to be at the green square. It actually happened up here, and just very rapidly, as you see right here, he takes his mouse and he says it happened there. In just a matter of seconds, we've calibrated the system, and there's an image that was acquired afterwards. Okay. So a little bit more about our RF pictures. Here's a comparison of the RF picture on the top with a thermal ablation picture at the bottom. So this was the thermal ablation at the same position as that RF was obtained. And what we see is if we look over 5 ablations and we look at the position of the thermal ablation versus the position of the RF, that in the X direction, which is not the direction of the motion, that we're pretty good in terms of having the same position within a millimeter. And then we're not too bad in the other direction, but 3 millimeters is probably because this image is potentially at a different point in the respiratory cycle. Okay, and we're able to then calibrate that focal spot with just a fraction of the energy that a test spot would have required. All right, so we come back one more time and look at the reflection data. So this is the screen showing you the RF picture over here, and over here we can project what the the reflection information is telling us. And here's an example where we have reasonable RF depiction right there, but the reflection data is telling us that there's actually quite a lot of reflected sound and that we don't have perfect coupling. Now at this point we have a choice. We can either turn off some elements or we can do some repositioning of the transducer in order to try to get a little bit better coupling. And what you see now when we do improve the coupling is that the RF picture is showing us much, much more displacement, in fact overwhelming the color scale that we were using right here. And so we find that the RF is a very rapid way to calibrate our setup, and in addition it's very, very sensitive, and we get, even when we have poor coupling, we can get very good depiction of the spot, and it's really going to give us a good way of evaluating how well we're doing. And not only that, but to decide how to perfect things a little bit more. So some fine-tuning that we might do, for example, is turn off elements based on the reflection. For example, if we're over ribs, if we place the device over ribs, we could look at the reflection data and turn off elements over the ribs, and then we could look at the RF picture in order to see how well it is, how good it is, and whether or not it's good enough to continue on. All right, let me move on. At this point, we need to collect some baseline data. So we use the hybrid multi-baseline referenceless processing algorithm. At this point, what you see in the movie is choosing the frame region of interest, or the area over which we do the referenceless portion of the processing. And so we chose a nice area there in the liver, and it was very interactive. At that point, we now move on to collecting our multiple baselines. These were done with the single-shot EPI image, and of course we're going to acquire multiple baselines at different at all these different positions of the respiratory cycle. And so we're collecting multiple baselines now, and then we can move on here. He can evaluate how good those baseline images were very rapidly, and at that point move on to the ablation. Okay, so this is actually a volunteer rather than one of our porcine experiments, so you're not going to see any ablation. But what this is showing you is what the display looks like. And so again, we have our thermometry that's being updated in pretty rapidly here with 3 to 8 frames per second. And we can choose whether we want to look at this image or this image over here, or we can change our frame region of interest to a different location or different orientation. And almost finished here. I want to finish up with just showing you some example ablations. And so these were 6 different ablations in the porcine liver. And so these are showing you pretty small focal spots. And so this is somewhat of an indication of how well the steering is doing. Unfortunately, the lesions are a little small, and so one thing that we do need to do is to go back and try to make larger lesions, and it is possible that the steering may be a little imperfect, and that if we do a better job than that, we'll get larger lesions as well. In addition, we think that if we go to higher frequency, then that could, of course, help us with getting larger lesions. Okay, so just to conclude, we believe free-breathing liver treatments are very complicated, but they're quite possible. We're demonstrating some tools, in particular the MR-ARFI, which we think will play a substantial role in the setup and calibration of free-breathing procedures in the liver. We also think the hybrid multi-baseline references thermometry is very, very important, and unfortunately I didn't have the time to go into too many details on that. So we're building an application-specific interface based on the real-time imaging that allows us to give control over the imaging and the ultrasound in order to tailor the workflow to the free-breathing liver application. And just lastly, we believe that free-breathing focused ultrasound liver treatments do look to be realistic. So I'd like to acknowledge my grant support. In addition, I'd like to acknowledge Andrew Holbrook up here in the green shirt, as this is his work that I am representing today. Thank you very much.